Hi, I'm Nancy from Small Lab at UT Arlington. I'd like to share a simple idea with you today. In multimodal alignment, the geometry of your similarity space matters more than the architecture sitting on top of it. A one-line change in the geometry gives us the SOTA result and the short video text retrieval. We call our method HyperGRAM. Multimodal alignment today is dominated by two ideas. The first is the clip. It circles modality in piles, text and video, text and audio, video and audio. 3 circles, no joint view. It's like judging a chart by listening to each single alone. You miss the harmony. The second is gram. It uses one volume across all modality at once, elegant, and it captures high-order correlations. The gram lives in flat Euclidean space, and that's exactly where it breaks. Here is what goes wrong. After L2 normalization, the gram matrix becomes almost the identity. So the determinant collapses to 1 for every sample. Look at the Euclidean histogram. The standard deviation is just 5 thousandths. There is no signal left. Now switch to hyperbolic geometry. The volume spread out across a wide range. That's about 295 times more variance. The signal is back. So why does curving bring the signal back? The reason is capacity. Think about how many video and audio pairs could fit in description. A dog, a few dozen. Now think about a rich one more. 1,000. We call this interpretation space, and it grows exponentially with semantic richness. Hyperbolic space also grows exponentially. Euclidean space grows only polynomial. So to host an exponentially large set, you need an exponentially growth space. Our lemma proves this. Hyperbolic volume proves variance. Euclidean volume have 2 couplets. The couplets isn't a bug, it's a theory. So the obvious next move is to go fully hyperbolic. We project each embedding onto the Lorentz hyperboloid and recompute the volume. But here is the surprise. Pure hyperbolic doesn't consistently beat Euclidean gram. On some datasets, it actually drops. Why? Because the two geometry do different jobs. Euclidean gives stable separation between categories. Hyperbolic gives a fine-grained variance within a category. Neither alone is enough, so we use both. So the pipeline, same encoders, same fusion, same training pipeline. The only change is how we compute the alignment circle. We compute the volume in both geometrics, then mix them with a single learnable weight across all 4 datasets. This weight coverage to about 1/2. We didn't design that. Gradient descent discovered. The model itself is telling us both geometry contribute equally. The cost, unscalar, and the 3% extreme training time. Though architecture changes, a drop in replacement for cosine similarity. Though short video text to video retrieval on 4 standard benchmarks, VATEX sets the pure bar. Gram is competitive, but bounded by the color path. Pure hyperbolic ties or lose. HyperGRAM, the hybrid, wins every single benchmark, plus 1.8 on MSR-VTT dataset, plus 1.5 on DiDeMo, plus 2 on ActivityNet, plus 2.9 on VATEX. And critically, the gains go with the number of modalities. More modalities means more high-order structure to capture, exactly what the theory predicts. And one last check, do the volume actually reflect interpretation space size? MSR-VTT dataset simple caption gives a volume of 2.08, reach negative to give 2.38. That's a clean 14% increase. An interesting case is DiDeMo. The correlation is negative. That's not a failure, it's a feature. DiDeMo descriptions looks like person walks, sit down, head appears, more words, but fragmentary event, smaller interpretation space, smaller volume. Volume tracks semantic structure, not word count. To recap, pairwise cosine missing joint structure, Euclidean volume captures the structure, but they collapse under L2 normalization. Pure hyperbolic restore variance but lose stability. So we use hybrid geometry combine both. One-scalar for SOTA result, and the geometry you choose really doesn't matter. That's all. Thank you.